Now there's something? Yeah, because I changed the microphone. Hello, hello. Now it should work. Now it should work. Yes. Yes. Okay. Okay. It's working now, right? All right. Okay. So we talk about 3D space. I will not repeat it. And then we see some examples of how this Hamiltonian works in 3D. And then we'll see. We look at the Gaussian, which is what I did in the lecture I recorded yesterday. So I'll do a bit of recap of what we did there. So it doesn't matter if you didn't watch it live. So we've been talking about 1D continuous systems, which were described like this. Span of X. Right, and then we saw, oh, we can choose different bases, so you can also choose this. Okay, and the main thing here was that we chose bases such that the inner product is this exponential, x h bar, which meant that transforming from one basis to the other was just a Fourier transform, right? And then just to put one more thing here, so the wave function for position was given by the inner product of the state with the position that we're interested in. And the same for momentum wave function. What's this, right? And maybe I'll also add here some operators that we looked at. So we looked at position operator, momentum operator, and we saw also how they acted on the wave function. For example, we saw this, that this was minus I h bar in the x derivative of the wave function. If you do it twice, you get the second derivative. And so on. And the main thing about them was that the commutator was a constant. Right, and from here we computed a bunch of commutators. So now, how do we go from 1 dimension to 3 dimensions? All turns out to be very simple. So you just take the tensor product for 3D space. You just build a Hilbert space that is 1 dimension along X, 1 dimension along Y, 1 dimension along that. which is where each of them is a copy of this thing here. Okay, so this is span of X. And so we give it a different name. But it's a copy, right? So X is in R. Something. So it's 3 copies of this 1D thing. Each of them also has a P basis. And we're just going to give it different names for each of them. So this is the span. We call it Px, so P in the X direction. Sorry. And the same here. So this is the same as Py. And here the same, right, for Pz. And each of them satisfies this in the product, right? So X dx is e to I X dx h bar. And the same for Y and Py, and the same for Z and Py. Okay, so they're kind of independent. Each of them is in their own Hilbert space, which is the same as we saw before. Okay. So because we might not want to be writing X, Y, Z all the time, we can come up with some shortcut notation. So if you look at the basis of this space, well, this is a span of. So I'm just multiplying all those things there. So it's the X. It is small x, it is big X. Y. Y. Z. The elements have this form with some coefficients. And instead of writing this all the time, we can define the position vector, which is just 3 coordinates. So then we can define the state R, which lives in the big space. So 3D sometimes called X, Y, Z. So this lives in the X, Y, Z space, which is just X times Y. So this is just which lives in X, Y, Z. What is R belongs to 3-dimensional space. And similarly, the same for momentum. So we write the momentum vector. It's just that. So then we can write P, which lives in the whole space, is X on X. Good. So I write the subscript a lot here because it's useful to keep track of whether we are working on a small space, on just one direction, or on the global space. But once it's obvious, you don't need to write it all the time. So far, so good. So what's the wave function? Well, going to go as usual. So this is just going to be our the same as there. It's just the inner product with R, and the same for the momentum wave function. It's just going to be P. But it's better to see why. So let's just see an example. Well, not an example. So I write the state X, Y, Z, right? And now, okay, it's the same state with the identities before. Right, the identities are not doing anything, and here I put the state again. Now I can, no. I can expand each of these identities. So each of them, this is dx, x. So this is in the x space. Another one for gy, yy. And another one z, z. Yeah. And now here comes my space, my state. Okay, and now I'll erase the board. So now I just expand each of these terms, and we'll get the usual inner product like we did in the 1D case. So let's raise up to here. Okay. So I just take all these integrals. And this is the same as having them all here. With dx, dy, z. And then what's left? I mean, I can do it in 2 steps just so we have this. There's this. There's this. This whole thing applied on my state. This is an x, y, z. Okay. And now, if you remember how the inner product works, we can split this thing. So I put the 3 integrals here. They're all from -infinity to +infinity. So we have here x tensor y tensor z. And then what we have on the other side is x, y, z. All of this applied on the state. But this I can simplify now. The state is in x, y, z. Look, this is my state R. And this is also R. But in this here, I can also call the R. So then, up a bit, I can simplify the whole thing to just have, well, I have the integral in R3, the R, R, and then I have this R chuk, and this is what I call the wave function point R, right? So again, I just took the state and I decompose it into a basis, the position basis, and the coefficient is the wave function at this position. So far, so good. What's next to see? Well, we need to see if the inner product still works. And then we need to see what operators we have in this 3D space, right? So we see the inner product first. Let me erase here. I still want to keep that. Okay. Where was I? So now I have this 3D space, and I want to know what's the inner product between an R vector, so position vector and the momentum vector, but now in 3D. Well, this, I just expand them. So this is X, Y, Z, each in their space. And here we have the X, Y, Z, each in their space. And the inner product works like each in their subsystem. So we have XPX times Y PY times Z. Is that right? And each of them, we know from there what they are, right? So this is E to I X, the X of H bar. This is E to I Y, PY over H bar, normalized. And this is E to I Y, so Z, Z of H bar. Okay. So we just put all the normalization constants to one side. So there's 3 of them, minus because it's in the denominator, and 1/2 because it's on the square root. And then we have E to I over H bar, and then we have XPX plus Y PY plus Z PZ. But this thing here, this is just in the product between our 2 vectors that we started with, the R talk. This is a dot in the middle, P, right? So the inner product between R and P is the normalization coefficient. Now it's the cube of what it used to be, and then I over H RP. So I'll just write it here, and then we move on. Okay, so we had conclusion was that this inner product between R and P is E to R, inner product between two vectors, R divided by this 2 by H 3 halves. Okay. So now what operators do we have in this 3D space? Well, we have the same as we had before, but now we need to consider them in the global space. So what we say when we mean Px now is Px acting in the first system and nothing happening in the y and z directions, right? And the same for Pi becomes identity on the first system, Pi in the second. And this is just a normal P operator like we had before. And the same for Z. One, two identities, and PZ, right? So this is Y. So how do they act on the wave function? This is what you'll do in the tutorial. That if you do PZ, or by PZ now I mean this whole, sorry, PX. By PX I mean this whole thing. That is minus the derivative in order of x of the wave function that depends on x, y, and z. So it depends on the 3 coordinates. So this is what you'll prove in the tutorial, and the same for the other two. Py. Like this. And the same here, okay? Exactly the same. Good, but these are, so we do the same for the position operators. And then there's one operator that we care about, which is the square of the momentum, because we need it in the Hamiltonian, right? So so for position operators, it's the same thing. X, what we mean by X is always this. And Y in Z. Then we have something we call Y, which is, again, just the position is the same position operator, but just by a different name. Acting on the second system. And Z. Now, one operator that we care about, like I said, is P square. And so this is just the square, the sum of the squares of everything. So it's going to be Px squared. Yeah, by the way, sometimes people talk about, no, I will not go into this. No. This is Ps squared, which is Px times the identity square. That's just the identity square. Plus, py squared. So it's just the square of these things. How does it act on the wave function, which is what we'll need to know later. This, you'll do it in the tutorial. That when you have r p squared, and then the wave function, I mean, you can see how it works because you just expand p into this, then you have the three linear terms, and you know how each of them acts on the wave function. So then it's just going to be the sum of the three. And this is going to be minus h squared. And then you get the three derivatives. So you get px squared, dy squared, squared of the wave function position. If you wanted to know how it acts on the momentum here, on the momentum wave function, then it would be px squared plus py squared plus pz squared. So this thing sometimes we simplify with the symbol, that's all, right? So it's okay. And how do the commutators work? You also do it in a tutorial because it's very simple, but we can just sketch out how it works here. So let's look at some examples. For example, between x and px. Well, what's this? This is x times the other identities. And then we have times the other identities, and then you can do this explicitly. But because of the way the product of matrices work with tensor product, this is the only thing that's going to matter. So in the end, it's going to be just a commutator between these two times the identity on x times the other two identities. So just the whole identity. Okay, this you do in the tutorial as well, explicitly, but you can kind of believe it. And if I do it for different systems, for example, I want x and p of y. Well, this we know that this we know from before that operators that act on different Hilbert spaces, on different subsystems, always commute. So x is only acting, x is only acting on the x subsystem, and py is only acting on the y subsystem. So this whole thing commutes. So in general, it's going to be if you're talking about two operators that act in the same subsystem, then you get the usual commutation relations. And if they act on different subsystems, it's 0. And if it's a linear combination of this, then you do the linear combination. That's all it is. And now with all the ingredients to talk about the free, some Hamiltonian in 3D. And of course, we start with the simplest example. Yeah. So, sorry. Yeah, say again. If they only act on different subspaces, then they always commute, yes. Yeah, yes, yes, yeah. So this is true for all the others, right? So, yeah, so I just need a good, so if it's the position operator for the subsystem K, so this would be X, Y, or Z, and P for subsystem J, and that's going to be I H bar identity times the delta JK. Yeah. Sorry, this is P acting on subsystem J, so PX, P. Yeah, we did the piece up there. So that's what I mean by PX is that. Yeah, let's not go there. Some people talk about the vector P, which is all of them. But this is not a vector. This is just an operator. This is like the definition, okay? There is a version, but we don't need it for now. Yeah. The thing is that people can define the this thing as Px, Py, Pz. And then this P squared is just the inner product of the thing with itself. So this gives this ish. But we don't need it for now. Okay. So now, yeah, the reason why I defined the P square is because we need it for the Hamiltonian. So let's just write the Hamiltonian. So now we have H, still the momentum squared, which you move, and now we can expand it like this. So then we have its X squared plus the part on y squared plus the part z. And it's useful to write it in this form because now what we can do is look at it and say, well, this is an operator that acts only on x. So I can call this hx. This one acts only on y. And this one acts only on z. So this is the case of a non-interacting Hamiltonian between three systems. Right, you have three different systems. Each of them has a local Hamiltonian that acts like the identity in all the others. And remember that we did this a few lessons ago, a few weeks ago already, that if you have a non-interacting Hamiltonian, then all the local observables only evolve locally, evolve independently of each other. Okay. So, yeah, I don't know if you remember. So if I have last time ago, that if I have some Hamiltonian onto subsystems AB, which is just HA times identity B. HB. Then what we looked at was like, now how does some observable O in A evolve in time? And what we found was, well, this is always the HAB OA at time t, but because we can split it into two parts and OA always commutes with the second part, well, maybe I just do it explicit here. HJ times OA, and OA is also an observable that acts trivially on B. Plus, I can even have it inside the thing. And this is always 0, because again, they're operators in different subsystems with the identity and the rest. So what we saw is that local observables only care about the local Hamiltonian. Right, then we saw that we can get rid of the second part as well, doesn't it? Good. So this applies here, which means that if we have the free particle evolving, we can evolve the x direction and the y direction and the z direction independently, and then kind of combine it as long as we only care about the observables. And we're going to look at an example. Yeah, I'll just tell you first in general how we approach these systems, these problems. First of all, let's just talk about 2 dimensions, because it's the same going from 2 to 3 dimensions to 4 dimensions. You know, the only thing that changes is how many times I write px, py, pz. So let's do 2D example. And just for simplicity, if I have some object that's moving in one direction, so suppose that this is my coordinate axis. Okay. For simplicity, if I have an object that's moving in that direction, this is like the initial velocity. This is like classically, okay? Going there, and I don't have any good reason to have like this as a preferred direction. I'll give you an example later. What we do is to just take a new coordinate system to make our life easier. And just say, well, this is my x direction, and this is my y direction. Just align it with one of the directions, because this will just simplify all the calculations, right? It's just a physicist way of making our lives easier. When is this not always the case? When don't we do this? Well, I don't know, if there's some force, if there's like gravity with some force pulling down in this direction, then I might want to keep this as one of the axes. But if there's nothing, and in this case, we just have a free particle moving in that direction, so there's nothing else. So I let it, I just gonna align one of the axes with y. And by the way, just as a note for later, there's many ways of breaking up a big Hilbert space into tensor products. So I can write that my 2D thing was according to these original coordinates, x, y prime. And this is equivalent, meaning that there's a one-to-one map between the two. There's some non-trivial maths there, like this, right? This is something that is comes up a lot in quantum foundations, that you can take a big Hilbert space and break it down in different ways. And in this case, we just break it down in the way that's most convenient. So we're also going to take the simplest state we can have, and that's going to be a Gaussian in 2 dimensions, and it's going to be moving in one direction, and we'll see what to do with it. So maybe I'll go for a break now, and we start again at 10 past, and then we look at the example. Okay. Okay, so we have this Hamiltonian. Well, let's restart. And we're going to look at one particular kind of state, which is this very well behaved Gaussian state. So I'll just recap what he did in the tutorial and also what I said yesterday. So last time we talked about 1D Gaussian wave functions. So this is when the initial wave function, so the initial state, you can always expand it to x and times equals 0, x, and it was, this wave function is called a wave packet when it's of this form, eikx times some real function that's called the envelope function. So this is a wave packet. And in particular, when this thing looks like what's in, so this is a Gaussian function. So this is the envelope function when it is in particular Gaussian. That is root of 4 and then 2 pi sigma square. Well, what is Gaussian is not this, is the square of this. E2 minus something like this. I'm missing a sigma square here. I'm going to put it here, but I'm not sure. So it looks something like this, and what it looks like if you map on x is something like so, where resistance here somewhere in the middle, so that something like 60% of probabilities inside is the sigma, and the actual wave function, it has a real part and the complex part, and they both oscillate. So this would be like the real part of the wave function. And the imaginary part is the same, just a bit defaced. So, sorry, I lie a lot. this needs to go down as well. That's the module of the real part. So it actually oscillates like this, like the cosine, because the cosine is the real part of that, and the okay, and this would be the sine. Just imagine that is a bit out of phase. The sum of the squares gives the whole thing. Good. So this is the real part of the wave function. And this is the imaginary part of the wave function. T equals 0. Good. And that's a bad drawing. Yes? That could be here. Yeah, there you go. Found it. Okay. And then what we saw last time is how some properties of this evolve. And also you'll do in the tutorial this week how the wave function exactly evolves. So we saw how to do it, but then the actual calculation is a bit involved. So the x average of the position is this x0. So that's here. That's this x0 here. The variance, like I said, is sigma. So the square of the variance is sigma square. The momentum, initial momentum is given by this k, h bar. So that k. Delta p squared h bar for sigma squared. And then things evolved. So the evolution of x is the x0, like with the initial position, plus momentum on average divided by the mass times time. In this, we saw that it's 4 sigma mu. So it's given by that divided by mu squared times square. Okay. So if k is positive, it means that it's moving in this direction. So after a while, it's going to be like this, where the average position moves by this much amount, and the average variance, so the spread, also spreads up, right? So you can think now in 2 dimensions of something like this, that is this in 1 dimension and the same in the other, but as a preferred direction. So we're going to look in particular of a Gaussian in 2D moving in the y direction. So if you want to think of it in 3D, just think that we're looking from the top and we're seeing here. And so here's our initial blob. It's going to move. This is y. That's z. Sorry, x. You can imagine there's some z, but we do in 2D now. So it's going to, this is the initial momentum that it has. So after a while, it's going to become a blob, kind of a bigger blob, but a bit more moved in this direction. Okay, so we'll do the calculation for this. And then there's several things we can do at this point, which we'll be doing the next 2 lectures. So one is going to be to say, well, this initial thing also had a spin. And now I go through a region here where I just couple the spin. I'll apply some special Hamiltonian that we'll see. And I couple the spin to the momentum so that this blob is going to split into 2 blobs. It's just a proposition of a blob that goes to the left and a blob that goes to the right, depending on the spin of the particle. Okay, this is the Stern-Gerlach experiment. We talked about this before. This is a way to measure the spin by measuring the position of the particle. So this is option 1. Option 2, that will do, well, let's see, maybe next week. He's like, oh, we have this blob here, this nice Gaussian blob. And I do a double slit experiment, meaning that, well, I only let it a little bit go here and a little bit go there. And then I see what happens after a while. What happens after a while is that, let's do them in different colors. Well, this blob is going to expand as well, continues going there. This blob going to expand as well. So then there's going to be some overlap between the two. And then is when it will matter that they're not blobs, they actually have these waves. And then what we see is the interference pattern, meaning that if you have this one and this one, then, for example, if this is just the real part where they have the same sign, the total wave function is going to be the sum of the two. So you get a peak. And when they have different signs like here, they have destructive interference, meaning that the sum is going to be 0, so you get nothing there. So then the total wave function is going to be something like this. And that's the diffraction pattern that we see, or the interference pattern that we see in the double slit experiment. We'll talk about this later. So today we're going to first write the initial Gaussian, evolve it until we get to this point, and then if we have time, we do this first experiment. And then next time we do that experiment, so we have some fun. Okay. So now I move to these notes. So now what is a 2D Gaussian? So initial state. We're just going to generalize that state to 2 dimensions. So we have X and Y. Dy. I know, let's do this. X, Y, equals 0. X space X, Y space Y. And now this thing here, well, I'm going to say it's going to be E I K Y I E I K X X. And then the envelope, it's going to be a Gaussian in 2D. So the normalization constant, because we have 2 of them, is just a square root, not the 4 square root. And I'm going to say it has the same sigma, so it has the same variance in X and Y directions. So it's just a multiplication of the 2 wave functions. So I get minus squared. And here I think it's just 2 sigma squares, but correct me if I'm wrong. Okay. So if you look at this part for say y0, and we look at the wave function squared at x, y0, time equals 0, modulum, then it's going to look like this around the x0. If I'm looking at the check at the position x0, so the maximum in x, y time equals 0 squared, then it's going to look exactly the same shape. And remember that inside we have all these oscillations. So we can also represent it in 2D. So imagine it's a probability map where here's like the x0, here's the y0. And now it's like darker the highest the value is of that, right? So if I was in a computer, I could do this very dark and here a bit more blobby and so on. Right, so it looks something like this. And now, because I said that the momentum is exactly this k, and I want it to be moving in the y direction, I'm going to say this kx is 0, so nothing is happening in the x direction. So if I do kx equals 0, then it's just moving in the y direction. So then I have x, y equals 0. It's just okay, y. And you know, because we only have, I leave it. Sigma squared. Okay. Now all the properties are as they were before. So x at time 0 is x0. Delta x squared at time 0 is sigma squared. Y at time 0 is y0. This is the same because I said it was the same sigma. P in the x direction is 0, but remember that it has some variance. P x at time 0. What was it? And y. Okay, and now the py is okay. So now we can evolve in time p and x, and like because of now we just put together all the ingredients, so we know how each of them evolve for the Gaussian, and we also know that to do the evolution of x, we just need to worry about the Hamiltonian in x, which is just a free particle in this direction. For y, we just have to worry about the free particle in the y direction, right? So we can just do directly that, well, x at times t, well, this is x0 plus the momentum in the x direction times time, but this is 0, so that's just x0. So if this was y and times equals 0, then we know that it's going to be centered somewhere here. So the x does not change at some time later. Okay. As for the y, at times t, that is going to be y0 plus the momentum divided by the mass times the time. These guys don't change like before. What changes now is the variance, and it changes in the same way for both of them. So delta x squared times t is delta y squared at times t, which is sigma squared plus h bar 4 sigma. So it's just like we did before that. So this means that later our blob is here. And it's just a bit more spread out. And you might wonder, like, you know, if I shoot a ball or a bullet in a direction, I don't see any of this spread. And I mean, just remember that this is all multiplied by h bar that's very small and divided by the mass. So unless your mass is very small, like at the same scale of h bar, then this term is going to be negligible, right? So that's what happens for macroscopic objects that are very heavy, even if they were described by a Gaussian wave function, which is the closest we have to a classical thing in the quantum realm. Like, it's just that this coefficient here is going to be very, very small as the mass increases. But for an electron or a photon, then you can actually see this, and it does make a difference that it spreads out. Okay. And again, note that, of course, the actual wave function still have all these oscillations, as you will see in the tutorial. But now let's do the first application that we talked about, this one here. Yeah. Yeah.
So since we can, like we did similarly with subspaces, we can approximate the continuous subspace with a very large discrete space, so we could technically do the same thing here.
Yeah.
With a 3D.
Yeah.
And then it would result in a convergence towards
Yes. Yes. Yeah.
And this is how it's going to practice.
I mean, in practice, we use the continuous case as because the maths are nice there. But for example, things like the Fourier transform, you also have the discrete case that you can use for very large discrete systems. So in practice, when making this kind of calculations, people normally use the continuous case, not the discrete. When we're talking about position, yeah. Because so what was the exact formula? I don't have it here. So it only depends on the variance in P. It does not depend on the value of P. So it was, let me see. So like the general formula that we did yesterday, I guess, was that this was delta x squared times 0 plus some beta that for the Gaussian is 0 plus delta p squared at times 0 divided by the mass squared T, and there might have been another constant, let's see. No, that's it, right? Yeah, that's it, squared. Okay, so this was in general for any wave function. So if you look at yesterday's class, that's what we do. So it does not depend on the initial value of momentum, just on the spread in momentum. And the spread in momentum is always there, because if you look at the initial wave function in momentum space, it's gonna, so if this is Px and this is Py, it's gonna be somewhere here. This little blob, where kind of the size of the blob before it becomes more and more diffused, this is going to be the sigma momentum. Sorry, the delta p x, delta p y at time 0, and that's that thing there. That's the square, so this is this size. So if I project it into Px, it's going to look like this. And in Pi, it's going to look like this, where this is the wave function of Px at the maximum of the other one, time equals 0. So the wider it is in position, the narrower it is in momentum, and vice versa. Okay, but the answer to your question is that the evolution of the variance in x only depends on the initial variance of t, of p, not on the initial value of p. Sorry, p, this should be around here. That's 0, and this is k h bar. Yeah, does that answer your question? Okay. Good, so now we evolve the blob. So now we're going to do the Stern-Gerlach experiment. So to start off, we say maybe my initial state now was the thing in x and y directions times something in spin. So alpha 0, S for spin. So my total Hilbert space is x and y and the spin of the particle. So some other property of the particle that I care about. In this case, I care about spin because it's a qubit. And we do this. Okay. So my initial Hamiltonian that we used so far, we can write it in the global space as it was like p squared in x and y, q mu times the identity in spin. So nothing happened to the spin. Okay. So now I have, at this point, I have this psi of t, and I still have this alpha 0 in spin plus beta in spin. Okay. And now I'm going to act with some interaction Hamiltonian, which is going to be like shooting a magnetic field. So this was the initial Hamiltonian in this area. So let's do here y. We have kind of 3 zones. Here's a zone of interaction. This was the H0, and here's going to be H0 again. So we did this part where I went from a blob here to a bigger blob there. And now we're going to apply this interaction Hamiltonian. And I don't know if I'll give you the exact form of the interaction Hamiltonian because you only have Oh, thanks. Oh, I will do this. No. Right, so I'll do interaction Hamiltonian. First of all, I want it to only act in the x direction, so I'll do an identity in y. And there'll be some edge interaction s and x here. Yeah, okay. And now we need to do the general case for this interaction Hamiltonians that we have not done so far. So I'll just do the beginning of this and then we'll see how it works. But I'll do first, sorry. I wasn't sure which of the two experiments I wanted to do first. That's why I'm hesitating a bit, but I'll give you the intuition for what we want to happen after this interaction time. Okay. What I want to happen is the same as we talked before when we talked about the C0 and measurements as unitary evolutions. So what I want it to happen is that intuition is that thus after the interaction, then I have, and just changing the order of the subsystems a bit, but that's why I write the indexes here. Times, oh, I don't, sorry. L 0 in the spin plus beta R minus B. Okay, what I'll do, let's do today this part. Okay. For today, here it is. For today, you believe me that after this interaction, we have this state. And now we're going to just evolve this state and see that we're going to get one blob here and one blob there. Okay? And on Thursday, we will look at what this exact interaction Hamiltonian is and how we obtain this state. Okay? And what I want from this state is that this is a Gaussian again. And so is the other one. But here I have that Px at this time t prime, so after interaction of prime. This is h bar times a minus, and py is the same, h bar ky like before. And I want this one to be Px h bar a positive and py being h bar k. Yep. Okay, so this is the goal. After the interaction, I want the total wave function to be a superposition of two things. So remember, let me do the classical, the discrete analogy once, was if you remember that if you have the C0 gate, if you had some original system in state alpha 0 plus beta 1, this is the first system, and the second system in 0, then this goes to alpha 0 0 plus beta 1 1. Now this is my spin, and this is going to be my xy. Spin, xy, spin, xy. And what's changing here, sorry about that, this should be a 1 here. 1 spin. So what's changing here is that instead of the 0 and the y, what I want to achieve instead of 0 and 1 is that here, correlated with the 0 state of the spin, I have a Gaussian wave function that's moving to the left. So the momentum in the p direction is going there, is negative. And correlated with here, I have something that's moving to the right. So now we'll just apply the same thing and evolve it again. Okay. So if now my initial state, I'm going to see now how they evolve after that interaction region, right? So my initial state now is this superposition, alpha, I left, x and y, 0 and s, plus beta, I right, 1 in the spin, right? And the Hamiltonian is now again the h0, so the p squared over 2 mu, which means that my u of t is e minus p squared times, like so, right? So, and I want to know how it acts on this whole thing. And the key times the identity on S, right? And the key thing is that it acts linearly in a superposition. So my state after some new time t, so at the very top there, it's going to be u of t applied to the initial state, which is what? Well, this is alpha. Now, oh. Good. Alpha, that exponential, h bar 0, sorry, left, times the identity acting on 0, so nothing happens here, on a spin, plus beta e minus p squared h bar r answer 1 in the spin, right? xy, xy, xy. So the key thing here is that, well, the unitary is going to act linearly on the superposition, and in particular, it only acts non-trivially in the position and leaves the spin alone. And now we're just going to do as an approximation, seeing what happens here for the observables and what happens here for the observables. And we cannot always do this because of what we'll see next time, because there could be some interference effects that are trivial, that are not small. But in this case, I just make this constant a large enough that it evolves. So I'll do it individually, like as if we're just evolving psi L. So for psi L, what happens is the x at the position t is going to be the initial x. This was some x0, right? Like we had before, plus the momentum in x initial times mu, but this now is something. So it's minus h a over mu times. And the p sorry, the y position of identity is going to be, well, again, y0 plus h bar k over mu times, right? So this is for the psi L. The variance will also grow. For the right side, we have the right, we have that x is going to be x0 minus plus HA over mu t, and the y is going to be the same. Y0 plus. So if I think of them independently, I have these two blobs evolving, and their variance is also evolving. But if I make this A large enough, they're going to end up for like, so this is 0, and this is going to be minus A t over mu. This is going to end up like here, mostly here. The other blob is going to end up mostly here, and there's going to be some interference in the middle where you can maybe even have funny effects, but we don't care about it so far. So now, what is the probability of finding it on this side? This we're going to do more carefully later, but of course, it's going to depend on the alpha, right? Because that's like the whole weight of this branch. So it's the whole weight of the left side. And the probability of finding on the right side is going to depend on the beta, right? It's going to be beta squared, the whole branch of this. And of course, that if I find it here, I don't know. It could be a contribution either from the left or from the right. But if I find it here, then I have a very good chance that it was from this contribution. So next time, we're going to look at the exact interaction Hamiltonian, and then we're going to see exactly how to recover the alpha and the betas from the final measurement. And then we're going to look at the double slit experiment, and that's going to be it for the free particle. All right, thank you, and see you on Thursday here. Yes. I'll upload the lecture notes this afternoon. Right.
And also a question.
Yeah.
Because we have a lot of mathematical calculations going on, but there are fundamental physical principles behind it, which is this wave-particle duality,
Yeah.
which is the whole thing of the double slit.
Yeah.
But my question is, so when we had this qubit analogy at the beginning, we also measured it in a different basis, and the qubit is also like a wave and the particle, because probability distribution in the basis corresponds to wave. So when we measure the qubit in a basis, we basically force the way to be decomposed in this basis. And the question is, could we measure the qubit also continuously?
The
double slit, like here we measure continuous.
Yeah, what we measure in the end is the position. Yes, yes. I mean, you are measuring a qubit using a continuous measurement, essentially, right? You're doing an indirect measurement of the qubit.
Here.
Yeah. Yes. Yeah. I mean, I'll make it more explicitly, if not on Thursday, then next week. But what we measure at the end is the position of the particle, right?
Yes.
We use this to infer some information about the qubit.
And a particle consists of qubits which have a position in space.
Yeah. So the particle consists of 3 Hilbert spaces,
Yes.
right? In this case, one for X, one for Z, and one that is a qubit,
Yes.
which is encode the property of spin.
Mm-hmm. And when we measure the spin, it measures. But we don't measure the spin when
we don't measure the spin directly, right? What we did was to couple the spin to something we can measure, which is the position. Which is the position. So if the particle is all in state 0, right? Alpha is 1, beta is 0, then we know that it goes there, which means that when we measure the position, we're going to find it either here or here or here or here. If you do this many times, every time prepare a new spin.
And the 0 spins, they would tend, 0 particles and the 1 particles, they would tend more
to the right.
So 1 tends more here and
Yeah.
0 tends more
Yeah.
here.
Yes. Because of the way we couple the spin and the
Yes.
and the thing. This I will explain slowly.
Yeah, just getting this should not just
Yeah. Let's bring this up.
Because I think without this, it's much more visible on the recording.
Yeah. Okay, that's good to know. I guess there should be some overlap.
I mean, normally the cameras are up there, so they don't have the shields in the picture.
Indeed.
But
Yes.
here it's a bit.
Huh.
It's a bit the wooden part.
All right. Thanks.
Thank you.
I should stop the stream.